1 minus 1. So you literally just strip off, and make it into a 2 by 2 matrix. What's my inverse matrix? Right? So if I calculate the, like the coordinate vector of, let's say, 3, 4, what would it be? I do, the basis matrix inverse times this 3, 4 vector, right? Which in this case is like 1/2, 1, 1, 1 minus 1. How did I write down that inverse? You guys know, right? I hope you know, because that's definitely on the test, right? 2 by 2 inverse formula, come on. If I don't test on that, for shame. Yeah? You guys do get like a, did I say page of notes or 3 by 4 5-inch card? 3 by 5 card, okay. Usually when I ask that question, it's always responded back with a page, no matter what I've said before. So, but thank you for not preying upon my ignorance. Let's see here, or lack of remembrance. So this is 7, and this is, what, minus 1? So that's 7/2 and minus 1/2, right? Or let me write it as a decimal just for the sake of foolishly attempting a picture. So what this says is that 3, 4 is equal to 3.5 times 1, 1 minus 0.5 times 1 minus 1. Is that true? We get 3.5 minus 0.5 is 3. 3.5 plus 0.5, it works, right? What's going on geometrically? We can try to picture this, right? So 3, 4 goes over 1, 2, 3, and up 2, 3, 4, right? So basically 3, 4 is this vector, right? And so we can see that as 3.5, 1, 1. So 1, 1, I need like a ruler. That's length what? Length 5. So if I did this right, it should be something. And that's, I think this is under it. So I think it's something like this, roughly speaking. And then 1 minus 1, I didn't do it quite right. It's kind of like, I think it's more like, I don't know, I'm trying, guys. This one, 1 minus 1 would be like this, right? But it's minus, so I didn't do this right. I don't know, so it should be something like this. I should have done these first, then it would have been more aggressive. So the point is to build this 3, 4 vector, right? You do 3.5 the 1, 1, and then minus 0.5 the other one. You could let's see here. Well, let's see here. I'm trying to think of notation I want to introduce for you guys. So suppose I guess I could draw a picture something like, here's y, here's x, right? And I guess in my current notation, we have the coordinate vector of C1, 1, 1 plus C2, 1 minus 1 is what? C1, C2, right? Did I never move the camera over here? Okay. Yay. All right, so let's think about this. What's the equation? Let's think about this carefully. If you want to, what's the equation for the x-axis? Ever think about this? The equation for the x-axis is y equals to 0. What's the equation for the y-axis? X equal to 0, right? What's the equation for the C1 axis? C2 equal to 0, right? So I think the way to understand that is you could picture it kind of like this. This is the C1 axis, right? And the C2 axis goes like this. They're actually at right angles. Did we talk about dot products yet? A little bit. So if you take the dot product of these two, you get 0. They are perpendicular. But they're not length 1, right? Like, check this out. The C1 and C2 coordinate system, a lot of people wouldn't like this coordinate system. It's not a very good coordinate system in some sense because it doesn't preserve our usual idea of distance, right? Like this point right here, 3, 4, you guys told me, distance how from the origin? Distance 5, right? But we figured out that in C1, C2 space, we get this, right? How far, if you just take the square root of the sums of those squares, do you get 5? You actually don't get 5. You get something less than 5, I think. I don't think I have my calculator on me, but I'm pretty sure you get less. I'm pretty sure that if you calculated the square root of like 3.5 squared plus minus 0.5 squared, right, you'd get like, I think it's 5 over root 2. The reason that's happening is this basis is not normalized. So these basis vectors have length square root of 2. All right? So if you want the like distance from the origin to still be the same in the new coordinate system, you need to work with what's called an orthonormal coordinate system. This is not that. This is an orthogonal coordinate system, but it's not normal. So like the notion of distance between points is going to get all skewed. You don't keep the notion of distance as you change coordinates here to the C1, C2 coordinates. All right? So I'll show you more examples when we have more time, but we actually have just enough time to introduce, like, how would we change the formula for a linear transformation? Like, what if I want to write a linear transformation in terms of the new coordinates? Do you have any sense of that? Like, I'm trying to say here. Let me not just, I'm going to save that for another day. We'll do that another day. I'm going to do that here. That's a longer discussion. I shouldn't do that right now. Yep.
So in the first graph that you drew, are those black lines, is that like E1 and E2?
The black. Oh.
Like the standard basis vectors?
Well, this one, I mean,
Isn't that what your definition was saying?
well, yeah, I mean, let me look at it a different way. Maybe this will help you. So 3, 4 is this, right? 1, 2, 3, 3 of those. And then 1, 2, 3, 4 of those, right? So this is 3E1 plus 4E2, also known as 3, 4, right? So on the flip side, we can do like, well, let me try the blue. I can do minus 1, 1. So it should be like length. The length of 1 minus 1 is the square root of 2. So my lines for like one of those should be, well, it's half of it though. So it's something like this. All right, that's minus 0.5, 1 minus 1. And then apparently 3.5 right, of the, I mean, I'm the limits of my artistry. These are two different ways to get from the origin, right, to that point. The point is the point. No matter whether you describe it using the Cartesian coordinates, right, building the point as a sum of x of E1 and E2, or if you use it, or if you build the point as a sum of V1 and V2. Either way, it's the same point. It's just two different ways to get there. Why do we care? All right, why do we care? Like, why not just use Cartesian coordinates? Isn't that enough? Well, here's the thing. Well, I don't want to, I'll just tell you. It turns out that if we change coordinates for certain expressions, we can simplify the formula vastly. For example, we'll see a little bit later in the course that if I have something like x squared plus 3xy plus 4y squared equals to 1, like if you look at that equation, right? What is that? Do you have any idea? I don't. What I know for sure is that it's not a standard like conic section. It's not a standard ellipse or hyperbola or parabola because of this right here. However, I know that this can be converted into something of the form lambda 1 times, well, let's say x bar squared plus lambda 2 times y bar squared equals to 1. Where here, x bar, y bar are equal to, let's say, beta bar inverse times xy. And this new barred coordinate system is what I would call the eigencoordinates for the problem. It turns out that there's a theorem that there always exists an eigencoordinate system which essentially diagonalizes the formula in this sense. It removes the cross terms, and in so doing, it reveals the true nature of the equation. If these are both pluses, it's an ellipse. If they're both minuses, there's no solution. If one is plus and one is minus, it's like a hyperbola, right? If one is 0 and the other one's not, it could be a pair of lines. It could be, I mean, there's a few different things that can happen, but basically that's it. So coordinate change is something we want to understand because it allows us to unlock the hidden true nature of equations. But the next thing I really should show you is how to change, how we find the matrix with respect to a non-standard basis is the next thing I was supposed to get to. But anyway, this is good for today.